let yourself sink deeper into comfort. Feel the weight of your body settling, your muscles releasing their tension one by one, starting from your toes and moving slowly upward through your legs, your torso, your shoulders. Take a slow breath, filling your lungs completely, and as you exhale, let any remaining stress dissolve into the air around you. Tonight, we're embarking on a journey to the edge of comprehension itself, to a structure so vast, so impossibly large, that its very existence challenges everything we thought we understood about the universe. But don't worry about following every detail or memorizing every number. Just let the words wash over you like gentle waves, carrying you into a state of deep relaxation while we explore one of the greatest cosmic mysteries ever discovered. Before we drift too far into the cosmos, I want to take just a moment to ask for your support. If you enjoy these journeys through science and space, if these videos help you unwind or fall asleep, please consider subscribing to the Science Pillow and leaving a like on this video. It helps more people discover this channel and allows me to continue creating these peaceful explorations of the universe's wonders. Your support means everything. Now, let's continue our voyage into the depths of space, where something impossible awaits. The discovery of something impossible. On an ordinary day in November 2013, a team of astronomers was hunched over computer screens, examining data that would forever change our understanding of the universe's structure. István Horváth, from the National University of Public Service in Hungary, working alongside John Hakila from the College of Charleston and Zsolt Bagoli from Eötvös University, was analyzing the distribution of some of the most violent events in the cosmos, gamma-ray bursts. These researchers weren't looking for the largest structure ever found. They were simply mapping where these brilliant flashes of energy appeared in the sky, trying to understand how matter was distributed across the universe. What they found defied belief. In the data, stretching across a vast swath of sky in the direction of the constellations Hercules and Corona Borealis, was a concentration of gamma-ray bursts that seemed impossible. The bursts were clustered together in a way that suggested something enormous lay in that region of space, something so large that it dwarfed every other structure astronomers had ever discovered. When the team calculated the size of this structure, the numbers seemed absurd. The clustering of gamma-ray bursts suggested the presence of a cosmic structure approximately 10 billion light-years in length. To put that in perspective, 10 billion light-years is more than 70% of the observable universe's radius. It's a distance so vast that light, traveling at 186,000 miles every single second, would take 10 billion years to cross it. When the light we now see from the far edge of this structure began its journey, Earth didn't exist. Our entire solar system hadn't formed yet. The light has been traveling through the emptiness of space for longer than our planet has existed. The team named this impossible structure the Hercules-Corona Borealis Great Wall, drawing the name from the region of sky where it appeared. A Filipino teenager named Jondrick Valdez from Marikina actually coined the term after reading about the discovery on Wikipedia, and the name stuck, though it's somewhat misleading. While the structure does indeed lie in the direction of Hercules and Corona Borealis, it spans far beyond just those constellations, extending through Lyra, Boötus, and Draco as well. Some astronomers prefer to call it the Great Gamma-Ray Burst Wall, emphasizing the method of its discovery, but the original name has become the most widely used. The discovery paper, published in the journal Astronomy and Astrophysics, sent ripples through the cosmological community. Here was a structure that, according to the prevailing theories about how the universe should be organized, simply could not exist. Modern cosmology rests on a principle called the cosmological principle, which states that on large enough scales, the universe should be homogeneous and isotropic. In simpler terms, if you look at a large enough volume of space, it should look roughly the same as any other similarly sized volume. There should be no preferred location, no special direction, no enormous structures that dominate vast fractions of the cosmos. Theoretical calculations suggested that structures in the universe shouldn't exceed about 1.2 billion light-years across. Beyond that scale, the universe's expansion and the distribution of matter should smooth everything out. Structures larger than this threshold would violate what's known as the end of greatness, the scale at which cosmic homogeneity appears, and individual structures disappear into the statistical noise of an evenly distributed universe. The Hercules-Corona Borealis Great Wall is more than 8 times larger than this theoretical maximum. But the story doesn't end there. In April 2025, more than a decade after the initial discovery, new research suggested that the structure might be even larger than originally thought. Dr. Jones, Hakila, and his team published findings indicating that the Hercules-Corona Borealis Great Wall could extend from a redshift of 0.33 all the way to 2.43. In the language of cosmology, redshift is a measure of distance and time. The higher the redshift, the more distant an object is, and the further back in time we're seeing it. This expanded redshift range translates to a structure that might stretch up to 15 billion light-years across. 15 billion light-years. The number is so large it loses meaning. Our minds simply aren't equipped to comprehend such distances. If you could somehow stand at one end of this structure and look toward the other side, shining a flashlight in that direction, the beam of light from your flashlight would not reach the other end until 15 billion years had passed. By the time that light arrived, assuming the universe continues as it has, our sun would have died, swelled into a red giant, and consumed the inner planets billions of years ago. Life on Earth, if it still existed anywhere, would have evolved, flourished, and potentially gone extinct multiple times over. The researchers noted something particularly intriguing in their latest analysis. They found evidence that the closest parts of the Hercules-Corona Borealis Great Wall might actually lie nearer to us than previously identified. This doesn't make the structure smaller. Rather, it suggests that this immense concentration of matter extends across an even broader range of cosmic history than we thought. Parts of the structure are relatively nearby in cosmic terms, while other parts stretch back to when the universe was less than half its current age. How do we know this structure is really there? How can we be certain that this isn't just a statistical fluke, a random clustering of gamma-ray bursts that happens to look like a pattern but isn't actually connected? These are crucial questions, ones that scientists have been grappling with since the initial discovery. The answer lies in understanding what gamma-ray bursts are, how they form, and why their distribution in space can reveal the underlying structure of the universe itself. Understanding cosmic scale. Before we can truly appreciate the enormity of what astronomers have found, we need to build up our sense of cosmic scale step by step. Starting from distances we can at least conceptually grasp, and working our way up to the incomprehensible. Let's begin with light itself. Light is the fastest thing in the universe, a fundamental speed limit built into the very fabric of space and time. In the vacuum of space, light travels at approximately 186,282 miles per second. That's fast enough to circle Earth's equator more than 7 times in a single second. If you could flip a light switch and somehow watch the light travel, it would reach the moon in about 1.3 seconds. The distance light travels in 1 year. Racing through space at this incredible speed every moment of every day is what we call a light year. 1 light year equals approximately 5.88 trillion miles, or, if you prefer, 9.46 trillion kilometers. It's a distance so vast that no human has ever traveled even a tiny fraction of it. The farthest any human-made object has traveled from Earth is NASA's Voyager 1 spacecraft, launched in 1977, and after nearly 5 decades of continuous flight through space, it has covered a distance of about 22 billion miles. That sounds impressive until you realize it's traveled less than 0.4% of 1 light year. At its current speed, Voyager 1 would need more than 17,000 years to cover 1 light year of distance. Now, let's scale up to our home galaxy, the Milky Way. This beautiful spiral of stars, gas, and dust stretches approximately 100,000 light years from edge to edge. Somewhere between 200 billion and 400 billion stars call the Milky Way home, each one potentially surrounded by planets of its own. Our Sun sits in a relatively quiet suburb of the galaxy, about 26,000 light-years from the galactic center, nestled in a minor spiral arm called the Orion Spur. If you could board a spacecraft that travels at the speed of light, an impossible feat according to the laws of physics, the journey from one edge of the Milky Way to the other would take 100,000 years. Think about that for a moment. All of recorded human history, from the first cuneiform tablets pressed into clay in ancient Mesopotamia to every event that has happened since, spans only about 5,000 years. You could fit all of human civilization 20 times over into the time it would take light to cross our galaxy. Our galaxy doesn't float alone in the void. It belongs to what astronomers call the local group, a collection of more than 50 galaxies bound together by their mutual gravitational attraction. The largest member of this cosmic neighborhood is the Andromeda Galaxy, a majestic spiral similar to our own Milky Way but slightly larger. Andromeda lies approximately 2.5 million light-years away from us. On a clear, dark night, far from the light pollution of cities, you can actually see Andromeda with your naked eyes as a faint smudge of light. That smudge is the combined glow of 1 trillion stars, so distant that the light reaching your eyes left Andromeda when our early ancestors were just beginning to walk upright on the African savanna. To span the distance between the Milky Way and Andromeda, you would need to line up 25 copies of the Milky Way end to end. In about 4 billion years, these two galaxies will collide and merge, their billions of stars passing through each other like 2 swarms of gnats, eventually settling into a new, larger galaxy that some astronomers have already nicknamed Milkomeda. But that collision is still far in the future. For now, Andromeda and the Milky Way maintain their separate identities, slowly drawing closer together across the vast gulf of space. The local group itself is just one small, part of an even larger structure called the Laniakea supercluster. This immense collection of galaxy clusters and groups spans 520 million light-years and contains approximately 100,000 large galaxies, with a total mass roughly 100 million billion times the mass of our Sun. Laniakea is Hawaiian for immense heaven, a fitting name for a structure so enormous that it encompasses dozens of smaller galaxy clusters, including our local group, the massive Virgo cluster, and the Hydra Centaurus supercluster. Now, let's talk about the Sloan Great Wall, which held the record for the largest known structure in the universe for several years. Discovered in 2003 by astronomers J. Richard Gott III and Mario Urich using data from the Sloan Digital Sky Survey, this structure is a vast wall of galaxies stretching approximately 1.37 billion light-years in length. The Sloan Great Wall is located roughly 1 billion light-years from Earth, and it represents one of the most massive connected structures in the nearby universe. To equal its length, you would need to line up about 13,700 Milky Way galaxies end to end. The Sloan Great Wall was impressive, a testament to the immense structures that gravity could build over billions of years of cosmic history. But even this enormous wall pales in comparison to what came next. The huge Large Quasar Group, discovered in 2012, measures approximately 4 billion light-years across. Then came the giant GRB ring, a circular arrangement of gamma-ray bursts spanning 2 to 3 billion light-years in diameter. Each of these discoveries pushed the boundaries of what cosmologists thought possible, each one uncomfortably large according to theoretical predictions. And then came the Hercules-Corona Borealis Great Wall. At 10 billion light-years across, and potentially as large as 15 billion light-years according to the most recent estimates, this structure is more than 7 times longer than the Sloan Great Wall. To visualize its size in terms of Milky Way galaxies lined up end to end, you would need approximately 100,000 to 150,000 of them. Picture that. 100,000 galaxies, each containing hundreds of billions of stars, each star potentially accompanied by planets, all of this arranged in a line that still doesn't capture the full scale of what we're discussing, because the Hercules-Corona Borealis Great Wall isn't really a line. It's a three-dimensional structure, a vast clustering of galaxies and matter distributed across an enormous volume of space. The distance from Earth to the Great Wall is approximately 10 billion light-years. The light we detect from this structure left it when the universe was only about 3.8 billion years old, less than one-third its current age of 13.8 billion years. We're not seeing the structure as it exists now. We're seeing it as it was in the distant past, a snapshot frozen in time by the finite speed of light. In the billions of years since that light began its journey to our telescopes, the universe has continued to expand. Stars have been born and died. Galaxies have merged and evolved, and the structure itself has likely changed in ways we can only imagine. To truly comprehend the scale we're discussing, imagine that every second of your life represents 1 light-year of distance. You wake up in the morning and 1 second has passed. 1 light-year. You eat breakfast, and maybe 5 minutes have gone by. 300 light-years, still nowhere close to crossing even our local stellar neighborhood. You go about your entire day, and by the time you go to sleep that night, about 16 hours have elapsed. That's roughly 57,600 light-years, just over half the radius of the Milky Way. To cross the Hercules-Corona Borealis Great Wall at this scale, where every second equals 1 light-year, would take you not hours, not days, not even years, but approximately 317 years of continuous counting. You would need to count 1 number every second, never stopping to eat or sleep, for more than 3 centuries. By the time you finished, generations of your descendants would have been born and died. Entire civilizations could have risen and fallen. And yet, impossibly, improbably, this structure exists. Against all theoretical predictions, defying our models of how the universe should be organized, the Hercules-Corona Borealis Great Wall stretches across a substantial fraction of the observable cosmos, challenging us to reconsider everything we thought we knew about cosmic structure, the cosmological principle, and why this shouldn't exist. The discovery of the Hercules-Corona Borealis Great Wall represents more than just a record-breaking measurement. It strikes at the heart of one of cosmology's most fundamental assumptions, a principle so central to our understanding of the universe that calling it into question threatens to upend much of modern theoretical physics. This principle is called the cosmological principle, and it states something that seems simple enough. When viewed on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means that the universe has the same properties at all locations. There's no special center, no preferred position. If you were somehow transported to a random point in the universe billions of light years from Earth, the universe around you would look statistically similar to what we see from our vantage point. Isotropic means that the universe looks the same in all directions. There are no special axes, no cosmic north or south pole, no direction fundamentally different from any other. These aren't just nice ideas that make calculations easier, though they certainly do that. The cosmological principle is a modern expression of the Copernican principle, the idea that we don't occupy a special place in the universe. When Copernicus argued that Earth orbits the Sun rather than sitting at the center of creation, he began a revolution in thinking that has continued to this day. Earth isn't at the center of the solar system. The solar system isn't at the center of the galaxy. Our galaxy isn't at the center of anything. As far as we can tell, there is no center. The universe doesn't have an edge or a middle. It simply is, extending in all directions, everywhere roughly the same. This principle allows cosmologists to make sense of the universe. It permits them to apply Einstein's equations of general relativity to the cosmos as a whole, treating the universe as a smoothly expanding fluid rather than a hopelessly complicated mess of individual galaxies and clusters moving in unpredictable ways. Without the cosmological principle, the mathematics of cosmology would become impossibly complex, with 20 variables and 10 interlocking equations that have no general solution. But with the cosmological principle, the equations simplify dramatically. The universe becomes describable by just a few parameters: its overall density, its expansion rate, and the properties of dark energy. This simplification has allowed cosmologists to build successful models that describe the universe's evolution from the Big Bang to the present day. Models that match observations with remarkable precision. Of course, nobody claims the universe is perfectly smooth on all scales. That would be absurd. Obviously, there are galaxies, which are much denser than the void between them. There are galaxy clusters, regions where hundreds or thousands of galaxies congregate under their mutual gravitational pull. There are walls and filaments of galaxies surrounding vast empty regions called cosmic voids. The universe is lumpy and irregular on these scales. The cosmological principle is a statistical statement. It says that if you average over large enough volumes, the lumpiness smooths out. Imagine a box of popcorn. On small scales, you might have regions where several kernels cluster together, and other regions that are mostly empty air. But If you take a large enough scoop, count the kernels, and repeat this process many times, you'll find that each scoop contains roughly the same number of kernels. The distribution becomes statistically uniform, even though individual kernels are clustered. So, how large is large enough for the cosmological principle to hold? This is where things get interesting and where the Hercules-Corona Borealis Great Wall becomes problematic. Studies of the large-scale structure of the universe, particularly observations of the cosmic microwave, background radiation, suggest that the universe should become homogeneous at scales of a few 100 million light-years. Beyond about 300 million light-years, the distribution of matter should be statistically smooth. However, there's a theoretical maximum to how large individual structures can be. This limit comes from understanding how structures form and grow through gravitational collapse. In the early universe, tiny variations in density, relics of quantum fluctuations from the earliest moments after the Big Bang, were amplified by gravity over billions of years. Regions that were slightly denser than average attracted more matter, becoming denser still, while regions that were slightly less dense lost matter to their surroundings, becoming voids. But this growth process has limits. The universe is expanding, and that expansion works against gravity's attempts to pull matter together. For a structure to form and remain bound together, gravity must overcome the expansion. The larger the structure, the harder this becomes. Calculations based on our best understanding of cosmic inflation, dark matter, and dark energy suggest that the maximum size for a single coherent structure is approximately 1.2 billion light-years. This threshold has been called the end of greatness. The Sloan Great Wall, at 1.37 billion light-years, was already uncomfortably large, just barely exceeding this theoretical maximum. The huge large quasar group at 4 billion light-years was harder to explain but could potentially be dismissed as a statistical fluctuation, or perhaps not a single coherent structure, but rather several structures that happen to be aligned. But the Hercules-Corona Borealis Great Wall, at 10 to 15 billion light-years, is impossible to ignore. It's not just slightly larger than theoretical predictions allow. It's more than 12 times larger than the supposed maximum. How can such a structure exist? Several possibilities have been proposed, each with its own implications and challenges. The most conservative explanation is that the Hercules-Corona Borealis Great Wall isn't real, at least not as a single coherent structure. Perhaps the clustering of gamma-ray bursts that led to its discovery is just a statistical fluctuation, a random pattern that looks meaningful but isn't actually connected by any physical process. Imagine throwing a handful of rice on the floor. Sometimes the grains will land in patterns that look like they mean something, even though their distribution is purely random. Could the gamma-ray bursts be like that? The discovery team and subsequent studies have argued against this interpretation. They've performed extensive statistical tests, including Monte Carlo simulations, where random distributions of gamma-ray bursts are generated thousands of times to see how often they produce clustering as strong as what's observed. The results show that the probability of the observed clustering being a random fluctuation is very low, typically less than 2%. While not impossible, it's unlikely enough that most astronomers take the structure seriously. Another possibility is that our theoretical predictions about the maximum size of structures are wrong. Perhaps there's something we don't understand about how structures form, or maybe our models of dark matter, dark energy, or cosmic inflation need revision. This would be a dramatic conclusion, potentially requiring rewrites of fundamental cosmological theory. But it can't be ruled out. The Hercules-Corona Borealis Great Wall wouldn't be the first observation to force scientists to revise their theories. The discovery of dark energy itself came from observations that didn't match theoretical predictions. A third possibility is more subtle. Perhaps the Hercules-Corona Borealis Great Wall is real, but not in the sense we usually think of structures. Instead of being a single gravitationally bound object, it might be what's called a supercluster complex, a region where multiple large structures happen to be aligned along our line of sight. Imagine looking at a mountain range from far away. From your perspective, the mountains might appear as a single, continuous wall, but if you could view them from above, you'd see that they're actually separate peaks. The Great Wall might be similar. Separate structures that appear connected when viewed from Earth but aren't actually physically linked. The debate over the Great Wall's existence and meaning has been vigorous. In 2016, a study by Sam Christian and colleagues argued that statistical biases in how gamma-ray bursts are detected and analyzed could artificially create the appearance of clustering where none exists. They pointed out that astronomers divided the gamma-ray burst data into 9 different redshift ranges for analysis, and when you look at 9 different ranges, the probability of finding something unusual in at least one of them increases. Think of it like flipping a coin 9 times. The chance of getting all heads is very low, but the chance of getting an unusual result somewhere in those 9 flips is much higher. A 2020 paper by researchers, including the original discovery team, addressed these concerns directly. They analyzed the most reliable current dataset of gamma-ray bursts and found that evidence for the Hercules-Corona Borealis Great Wall persists even when accounting for potential biases. Their analysis suggested that the structure is real, though they acknowledged that conclusive proof would require better data, particularly from the proposed Theseus satellite mission. Theseus, which stands for Transient High Energy Sky and Early Universe Surveyor, is a European Space Agency mission concept designed to detect gamma-ray bursts across the entire sky with unprecedented sensitivity. If launched, it would measure distances to thousands of new gamma-ray bursts, providing the high-quality data needed to either confirm the Hercules-Corona Borealis Great Wall's existence beyond any doubt or reveal that it's a statistical artifact after all. As of now, Theseus remains in the planning stages, its launch date uncertain. The controversy surrounding the Great Wall highlights a fundamental challenge in cosmology. We have only one universe to observe, only one set of data. We can't run experiments where we create new universes with different properties and see what happens. We're stuck with what we have, trying to infer universal laws from observations of our particular cosmic neighborhood. When something unexpected appears in the data, like a structure too large to exist according to our theories, it's genuinely difficult to know whether the theories are wrong or whether we're misinterpreting the observations. This uncertainty is uncomfortable for scientists and for anyone seeking definitive answers about the universe. But it's also what makes cosmology exciting. Every observation has the potential to overturn established ideas, to reveal that the universe is stranger and more wonderful than we imagined. The Hercules-Corona Borealis Great Wall, whether it's ultimately confirmed or refuted, represents this spirit of discovery and the willingness to question even our most cherished assumptions about the cosmos. Gamma-ray bursts as cosmic tracers. To understand how astronomers discovered the Hercules-Corona Borealis Great Wall, we need to understand the remarkable cosmic phenomena that revealed it. Gamma-ray bursts. These are some of the most violent and energetic events in the universe. Brief flashes of radiation so intense that, for a few seconds, they can outshine entire galaxies. Gamma-ray bursts were discovered by accident in the late 1960s, during the height of the Cold War. The United States had launched a series of satellites called Vela, designed to detect nuclear weapons tests by the Soviet Union. These satellites carried gamma-ray detectors that would trigger if they detected the characteristic signature of a nuclear explosion. On July 2, 1967, the Vela satellites detected a gamma-ray signal unlike anything they'd been programmed to recognize. It wasn't the signature of a nuclear test. It came from space. For years, these mysterious gamma-ray flashes remained classified. When they were finally announced to the scientific community in 1973, they sparked a revolution in high-energy astrophysics. What could possibly create such intense bursts of the most energetic form of electromagnetic radiation? The answer, it turned out, involved some of the most extreme physics in the universe. We now know that gamma-ray bursts come from two primary sources, both involving the deaths of massive stars. Long-duration gamma-ray bursts, which last more than 2 seconds and can continue for minutes, are produced when extremely massive stars, at least 20 or 30 times the mass of our Sun, reach the end of their lives. These stars have exhausted their nuclear fuel and can no longer support themselves against their own gravity. They collapse catastrophically, their cores compressing to form black holes while their outer layers explode outward in what we call a core collapse supernova. During this collapse, conservation of angular momentum causes the infalling material to spin faster and faster. Magnetic fields threading through this spinning material are amplified to enormous strengths. These powerful magnetic fields, interacting with the rotating black hole at the star's core, launch narrow jets of material perpendicular to the plane of rotation. These jets contain particles accelerated to nearly the speed of light, moving so fast that Einstein's special theory of relativity becomes crucial to understanding their behavior. When these relativistic jets punch through the star's outer layers and burst into the surrounding space, they produce the gamma-ray burst we observe. The jets plow into any gas or dust in the vicinity, creating shock waves that heat material to billions of degrees. At such extreme temperatures, the hot plasma emits copious amounts of gamma radiation, the shortest wavelength, highest energy form of light. For a few seconds or minutes, this dying star becomes one of the brightest objects in the universe. Short-duration gamma-ray bursts, lasting less than 2 seconds, have a different origin. These are thought to come from the collision and merger of two compact objects, typically two neutron stars or a neutron star and a black hole. Neutron stars are the crushed cores of dead stars, objects so dense that a teaspoon of their material would weigh billions of tons on Earth. When two neutron stars spiral together and merge, the event releases enormous amounts of energy, again creating powerful jets that produce a gamma-ray burst. These mergers are also the source of gravitational waves, ripples in the fabric of space-time that we can detect with instruments like LIGO and Virgo. In 2017, astronomers witnessed both the gravitational waves and the gamma-ray burst from a neutron star merger, a spectacular confirmation that our understanding of these events was on the right track. The key property that makes gamma-ray bursts useful for mapping the large-scale structure of the universe is their brightness. Because they're so energetic, gamma-ray bursts can be detected across enormous distances. Using current technology, Astronomers can detect gamma-ray bursts at redshifts of 7 or higher, corresponding to distances of more than 13 billion light-years. We're seeing these events as they occurred when the universe was less than 1 billion years old, in its early childhood. But why do gamma-ray bursts reveal the distribution of matter in the universe? The answer lies in understanding where and when these events occur. Both types of gamma-ray bursts require massive stars. Long-duration bursts come directly from massive stars at the ends of their lives. Short-duration bursts come from neutron stars, which themselves formed from massive stars that exploded as supernovae in the past. Massive stars don't form everywhere uniformly. They form preferentially in regions where there's a high density of gas and dust, the raw materials from which stars are born. These regions of active star formation are found in galaxies, particularly in galaxies undergoing bursts of star formation. And galaxies aren't distributed randomly throughout the universe. They cluster together along filaments and walls in the cosmic web, congregating in the densest regions while avoiding the vast empty voids. By mapping where gamma-ray bursts occur, astronomers can trace where large concentrations of galaxies exist, even at distances where the individual galaxies are too faint to observe directly. This is precisely what Istvan Horváth, Jon Hakkila, and Zsolt Bogoli were doing when they discovered the Hercules-Corona Borealis Great Wall. They weren't looking at galaxies themselves. They were looking at the distribution of gamma-ray bursts, using these brilliant explosions as beacons that illuminate the underlying structure of matter in the universe. Their analysis used data from several sources. The primary dataset came from NASA's Swift Gamma-Ray Burst mission, a satellite launched in 2004 that quickly slews to point at gamma-ray bursts when they're detected, capturing detailed observations before the burst fades. Additional data came from the Fermi Gamma-Ray Space Telescope and various ground-based observatories that followed up on Swift's detections, measuring the spectra of the gamma-ray bursts' afterglows to determine their distances. Distance determination is crucial. Gamma-ray bursts appear all across the sky, but to know whether they're part of a structure, you need to know their distances. Are they clustered in three-dimensional space, or do they just happen to be aligned along our line of sight? The key to answering this question is measuring redshift. As light travels through the expanding universe, its wavelength gets stretched by the expansion itself. Light that started out blue might arrive at our telescopes shifted toward the red. The amount of this redshift is directly related to distance. The farther away an object is, the more time its light has spent traveling through expanding space, and the more its wavelength has been stretched. By measuring the redshift of a gamma-ray burst's afterglow, astronomers can determine its distance with reasonable precision. Horváth and his colleagues had access to spectroscopic redshifts for hundreds of gamma-ray bursts, measurements precise enough to place each burst at a specific distance. When they mapped out the three-dimensional distribution of these bursts, they expected to see the lumpy but statistically uniform pattern predicted by the cosmological principle. And, indeed, much of what they saw matched expectations. Gamma-ray bursts were distributed across the sky roughly evenly, with the local concentrations corresponding to the cosmic web's filaments and walls. But in one region of sky, centered on Hercules and Corona Borealis, the distribution was anything but uniform. Gamma-ray bursts were piling up at redshifts between 1.6 and 2.1, corresponding to distances of about 10 billion light-years. To quantify how unusual this clustering was, The team employed sophisticated statistical methods. They used nearest neighbor tests to measure how close together the bursts were compared to a random distribution. They used bootstrap methods, where they randomly resampled their data thousands of times to see how often random chance would produce clustering as strong as what they observed. The results were clear. The probability that the clustering was just a statistical fluke was less than 2%. While not absolute proof, this was strong evidence that something real was there, that gamma-ray bursts were genuinely concentrated in this region of space, and that this concentration indicated the presence of an enormous structure in the matter distribution. More recent analyses, using larger datasets with over 500 gamma-ray bursts with measured redshifts, have further supported this conclusion. The 2025 study that suggested the Great Wall might be even larger than originally thought used improved techniques to account for potential biases, and still found strong evidence for the structure. They discovered that the clustering might extend beyond the original redshift range, potentially encompassing gamma-ray bursts from redshift 0.33 all the way to 2.43. The beauty of using gamma-ray bursts as tracers is that they provide a complementary view of large-scale structure compared to traditional galaxy surveys. Galaxy surveys typically observe relatively nearby regions of the universe where individual galaxies are bright enough to detect and measure. Gamma-ray bursts, being so bright, can probe much greater distances, revealing structure in epochs when the universe was much younger. They're also transient, appearing suddenly and then fading, which means they sample different parts of the sky over time. However, this transient nature also creates challenges. Unlike galaxies, which persist and can be observed repeatedly, gamma-ray bursts are one-time events. You can't go back and get more data on a specific burst once it's faded. This means that our map of large-scale structure using gamma-ray bursts is necessarily incomplete, limited by the bursts that happened to occur while our satellites were watching, and that were bright enough to detect and follow up with spectroscopy. This incompleteness is one reason why some astronomers remain skeptical about the Hercules-Corona Borealis Great Wall. They argue that we might be seeing a partially complete sample of a broader structure, or that observational biases might be creating the appearance of a wall where none exists. The counter-argument is that even accounting for these limitations, the clustering is stronger than would be expected by chance, and multiple independent analyses have confirmed its presence in the data. The gamma-ray burst technique for mapping large-scale structure represents a fascinating intersection of high energy, astrophysics, and cosmology. It takes our understanding of stellar death and turns it into a tool for measuring the universe's largest structures. Every gamma-ray burst is both a personal tragedy, the violent death of a massive star, and a gift to cosmology, a beacon illuminating the dark scaffolding of the cosmic web. The cosmic web. To truly understand the significance of the Hercules-Corona Borealis Great Wall, we need to zoom out and consider its place within the largest known structures in the universe, the intricate network known as the cosmic web. When you look at the night sky, stars appear as individual points of light scattered across the darkness. It's tempting to imagine that matter in the universe is distributed this way on all scales, randomly sprinkled through space like salt across a table. But this intuition is profoundly wrong. The universe is organized into an intricate three-dimensional pattern that resembles nothing so much as a vast spider's web, with galaxies strung along filaments surrounding enormous empty regions. This cosmic web wasn't always apparent. Through most of the 20th century, Astronomers knew that galaxies tended to cluster together, but they thought these clusters were more or less randomly distributed. The first hints that something more organized was going on came in the late 1970s and early 1980s, when astronomers began conducting large-scale surveys that measured the distances to thousands of galaxies, allowing them to plot the galaxies' positions in three-dimensional space rather than just their locations on the sky. The breakthrough came in 1989, when Margaret Geller and John Huchra of the Harvard-Smithsonian Center for Astrophysics published results from their redshift survey of galaxies. They had measured distances to thousands of galaxies within a wedge-shaped slice of the universe, extending out to about 600 million light-years. When they plotted these galaxies in 3 dimensions, the result was stunning and completely unexpected. Galaxies weren't scattered randomly. They traced out an unmistakable pattern of walls and filaments surrounding vast, empty regions. One particularly prominent feature, which Geller and Huchra dubbed the Great Wall, was a sheet of galaxies stretching across their survey region like a cosmic highway. This CFA2 Great Wall, as it came to be known, measured about 760 million light-years long, 200 million light-years wide, and just 15 million light-years thick. At the time, it was the largest known structure in the universe, but it was far from the last. As redshift surveys grew larger and deeper, mapping ever more distant regions of space, the cosmic web's full complexity began to emerge. The Sloan Digital Sky Survey, which began operating in 2000 and eventually measured distances to millions of galaxies, revealed the web in unprecedented detail. Enormous filaments, hundreds of millions of light-years long, connected dense knots where galaxy clusters congregated. Between the filaments lay cosmic voids, vast bubbles of space containing few, if any, galaxies, some of them hundreds of millions of light-years across. How did this structure form? The answer takes us back to the very beginning of the universe, to the first moments after the Big Bang. According to our current understanding, the universe began 13.8 billion years ago in an unimaginably hot and dense state. In those first instants, the universe was remarkably smooth and uniform, with matter and energy distributed almost evenly throughout space. But not quite evenly. There were tiny variations in density, differences of only a few parts per 100,000. Quantum fluctuations from the earliest moments that had been stretched to cosmic scales by a brief period of exponential expansion called inflation. These tiny density variations were the seeds of all future structure. Regions that were slightly denser than average had slightly stronger gravity, which attracted more matter toward them. As more matter accumulated, their gravity became stronger still, attracting even more matter in a runaway process. Meanwhile, regions that were slightly less dense than average lost matter to the growing dense regions, becoming the voids we see today. But visible matter, the stuff that makes up stars, planets, and people, constitutes only about 15% of the total matter in the universe. The remaining 85% is dark matter, a mysterious substance that doesn't emit, absorb, or reflect light. We know dark matter exists because we can see its gravitational effects on visible matter and on the path of light passing through space. Without dark matter's gravity, galaxies would spin themselves apart. Without dark matter, the cosmic web would look completely different. Dark matter played the dominant role in shaping the cosmic web. Because dark matter doesn't interact with light or with itself through any force except gravity, it could begin clumping together earlier and more efficiently than visible matter. While visible matter was still being buffeted by radiation pressure in the early universe, dark matter was already collecting in dense halos, forming the gravitational scaffolding along which visible matter would later flow. Computer simulations of cosmic structure formation beautifully illustrate this process. These simulations track millions or even billions of dark matter particles through the universe's history, following their movements under gravity's influence as the universe expands and evolves. The results show dark matter collecting along filaments, with the densest concentrations at the intersections where multiple filaments meet. These intersections become galaxy clusters, the largest gravitationally bound structures in the universe. The filaments themselves act as cosmic highways, channels along which gas flows from the voids toward the clusters. The simulations remarkably reproduce the web-like structure astronomers observe. They show how filaments connect dense nodes, how sheets of galaxies form where filaments intersect at angles, and how vast voids develop in the regions between these structures. The fact that simulations based on our understanding of dark matter, dark energy, and gravity can reproduce the observed structure of the universe is one of the strongest pieces of evidence that our cosmological models are fundamentally correct. But the cosmic web isn't static. It's actively evolving, driven by the expansion of the universe and the ongoing collapse of matter into dense regions. In the early universe, shortly after the first stars and galaxies formed, the cosmic web was more compact. The filaments were closer together, and the voids between them were smaller. As the universe expanded, the structures expanded with it, but the denser regions, held together by their own gravity, expanded more slowly than the voids. Over time, this differential expansion has stretched the cosmic web, making the filaments longer and the voids larger. Galaxy clusters sitting at the nodes of the cosmic web are still growing. They accrete new galaxies along the filaments that connect them to the rest of the web. Gas flowing along these filaments heats up as it falls into the cluster's gravitational well, glowing in X-rays that we can detect with space telescopes. The Virgo cluster, the nearest large galaxy cluster to us, sits about 54 million light-years away at the end of one of these filaments. Our own local group of galaxies, including the Milky Way, is slowly being pulled toward Virgo along a filament that connects us to it. Where does the Hercules-Corona Borealis Great Wall fit into this picture? According to the Discovery team and subsequent analyses, the Great Wall appears to be one of these enormous filaments, or possibly a complex of several filaments aligned in the same general direction. It's located at a distance of about 10 billion light-years, which means we're seeing it as it existed when the universe was only about 3.8 billion years old. At that epoch, the cosmic web was still developing, its structure less sharply defined than what we see in the nearby universe today. The gamma-ray bursts that revealed the Great Wall's existence are scattered across a region of sky, spanning about 1/8 of the celestial sphere, and concentrated in a redshift range corresponding to a particular epoch in cosmic history. This suggests that we're looking at a genuine concentration of matter, a region where the density of galaxies and star formation is higher than the cosmic average. Whether this concentration represents a single coherent structure or multiple structures that happen to be aligned is still debated, but either way, it indicates something important about how matter was distributed in the young universe. One of the most intriguing aspects of the cosmic web is how sensitive it is to the properties of dark matter and dark energy. Different models of what dark matter might be made of, or how dark energy behaves, produce subtle differences in how the web forms and evolves. by measuring the statistical properties of the cosmic web, things like how filaments connect, how large voids are, and how matter is distributed within filaments. Cosmologists can test these models and constrain the properties of the mysterious dark components that dominate the universe. The Hercules-Corona Borealis Great Wall, if it's real and as large as current estimates suggest, provides an important test case. A structure this large shouldn't exist according to standard models, which means either the models need adjustment or our understanding of the structure needs refinement. Perhaps dark matter behaves differently on these enormous scales than we thought. Perhaps dark energy's effects become important at earlier epochs than our models predict. Or perhaps the structure isn't quite as large or coherent as it appears, and more careful analysis will reveal it to be something our theories can accommodate. The cosmic web represents one of the most beautiful examples of how gravity, given enough time and space, creates order from chaos. From nearly uniform initial conditions, with just tiny variations in density, gravity has woven an intricate pattern spanning billions of light years. This pattern provides the environment in which galaxies form and evolve, the framework within which cosmic history unfolds. Understanding the web means understanding the universe itself, and every new discovery about large-scale structure brings us closer to that understanding. Dark matter and structure formation. The story of how the cosmic web formed is inseparably linked to the story of dark matter, the invisible substance that makes up most of the matter in the universe and provides the gravitational scaffolding for all visible structure. Dark matter was first proposed in the 1930s by Swiss astronomer Fritz Zwicky, who was studying the Coma Cluster, a collection of over 1,000 galaxies bound together by gravity. Zwicky measured the speeds at which galaxies within the cluster were moving, and used these speeds to calculate how much mass the cluster must contain to keep the galaxies gravitationally bound. What he found was shocking. The cluster needed to be about 400 times more massive than the combined mass of all its visible galaxies to explain the observed motions. Zwicky suggested that most of the cluster's mass must be in some dark form, invisible to telescopes but present through its gravitational effects. He called it dunkle Materie, dark matter. For decades, most astronomers dismissed this idea as unnecessarily complicated. Perhaps Zwicky's calculations were wrong, or perhaps there was some other explanation for the galaxy's high speeds. But as observations accumulated, the evidence for dark matter became overwhelming. In the 1970s, astronomer Vera Rubin measured the rotation curves of spiral galaxies, tracking how fast stars orbit at different distances from the galactic center. According to Newton's laws, stars farther from the center, beyond most of the galaxy's visible mass, should orbit more slowly, just as distant planets in our solar system orbit the Sun more slowly than close-in planets. But Rubin found that stars in the outer parts of galaxies orbit just as fast as stars closer to the center. The only explanation was that galaxies are embedded in enormous halos of invisible matter, extending far beyond the visible disk. Studies of gravitational lensing, where light from distant objects is bent by the gravity of massive structures in the foreground, provided further evidence. Maps of how light is bent show that mass is distributed differently than visible matter, with concentrations of mass appearing in regions that look empty. Observations of the cosmic microwave background, the afterglow of the Big Bang, show fluctuations in temperature that only make sense if dark matter was already clumping together when the universe was just 380,000 years old. Today, The evidence for dark matter is so strong that it's accepted by virtually all cosmologists. We know that dark matter makes up about 85% of all matter in the universe, or about 27% of the universe's total energy content when you include dark energy. We know it interacts only through gravity, not through electromagnetism or the strong nuclear force. We know it's cold, meaning the dark matter particles move slowly compared to the speed of light. What we don't know is what dark matter actually is. Despite decades of searching, we haven't yet detected a dark matter particle directly. The leading candidates are weakly interacting massive particles, or WIMPs, hypothetical particles that interact only through gravity and the weak nuclear force. Multiple experiments deep underground, shielded from cosmic rays, are searching for the rare occasions when a dark matter particle might collide with an atomic nucleus. So far, these searches have come up empty, but the hunt continues. Dark matter's importance for structure formation cannot be overstated. In the early universe, shortly after the Big Bang, visible matter was tightly coupled to radiation. Photons, the particles of light, were constantly interacting with electrons and protons, creating a sort of cosmic fog. Any time visible matter tried to clump together, radiation pressure would push it apart, preventing structures from forming. But dark matter doesn't interact with radiation. It was free to begin clumping, together immediately, driven purely by gravity. As the universe expanded and cooled, dark matter particles in slightly overdense regions began to slow down and collect, their mutual gravity pulling them together. Over time, these overdense regions became dark matter halos, ranging from small clumps the mass of Earth to enormous structures containing trillions of solar masses. These dark matter halos created gravitational potential wells, regions where space-time is curved by mass. When visible matter finally decoupled from radiation about 380,000 years after the Big Bang, it fell into these pre-existing potential wells. Gas collected in the densest regions, compressed by gravity until it became hot and dense enough for hydrogen fusion to ignite, forming the first stars. These stars clustered together, creating the first galaxies. The galaxies themselves clustered along filaments of dark matter, creating the cosmic web. Without dark matter, none of this would have been possible. Visible matter alone couldn't have clumped together fast enough to create the galaxies we see today. The universe would be a very different place, perhaps just a thin, diffuse cloud of gas with no stars, no galaxies, no planets, no life. Dark matter provided the gravitational seeds around which all structure grew. Computer simulations of structure formation have become increasingly sophisticated, tracking not just dark matter, but also the behavior of visible matter as it falls into dark matter halos, cools, forms stars, and is heated and expelled by supernova explosions and black hole activity. These simulations can now reproduce many of the detailed properties of galaxies and galaxy clusters, matching observations with impressive accuracy. The largest of these simulations, like the Millennium simulation and its successors, follow billions of dark matter particles through the universe's history. They show how small clumps of dark matter merge together to form larger and larger halos in a hierarchical process. The smallest structures form first, then merge to create bigger structures, which merge to create even bigger structures, and so on. This hierarchical structure formation is a natural consequence of how gravity works and matches the pattern we see in the cosmic web, where small galaxies cluster to form groups, groups cluster to form clusters, and clusters line up along filaments to create even larger structures. But there's a puzzle. While simulations reproduce the large-scale structure of the universe beautifully, they predict that there should be far more small dark matter halos than we see small galaxies. This is called the missing satellites problem. Our galaxy should have hundreds or thousands of small satellite galaxies orbiting it if every dark matter halo forms a galaxy, but we only see a few dozen. One explanation is that the smallest dark matter halos don't form visible galaxies because they're too small to efficiently cool gas and form stars. Another is that when the first stars and galaxies formed, they produced enough ultraviolet radiation to heat up and ionize the gas in the universe, preventing it from falling into the smallest dark matter halos. This is relevant to the Hercules-Corona Borealis Great Wall, because the gamma-ray bursts that revealed its existence are associated with star-forming galaxies. If there are regions where dark matter is concentrated but star formation is suppressed, gamma-ray bursts won't reveal them. This means the structure we're seeing through gamma-ray bursts might be only part of a larger dark matter structure. Conversely, if star formation is enhanced in this region for some reason, perhaps because the density is higher than average, or because conditions favor the formation of massive stars, we might be overestimating the true size of the dark matter concentration based on the gamma-ray burst distribution. Dark matter's role extends beyond just providing the initial gravitational wells. It continues to shape structure throughout cosmic history. As galaxies move through space, they carry their dark matter halos with them. When galaxies collide and merge, their dark matter halos merge too, creating larger halos that can hold even more massive galaxies or clusters. The distribution of dark matter determines how gas flows through the cosmic web, channeling it along filaments toward the densest regions where it can fuel star formation. In galaxy clusters, dark matter dominates the mass budget even more than in individual galaxies. A typical galaxy cluster might be 90% dark matter, with visible matter making up only 10% of the total mass. This dark matter holds the cluster together, preventing the galaxies from flying apart despite their high speeds. When clusters collide, their dark matter halos can pass through each other relatively unaffected, while the visible gas in the clusters collides and heats up, creating spectacular X-ray emissions that we can detect with space telescopes. The Bullet Cluster, a pair of colliding galaxy clusters, provides one of the most direct pieces of evidence for dark matter. Observations show that most of the mass in the system, as measured by gravitational lensing, is separated from most of the visible gas, as measured by X-ray emissions. This separation is exactly what you'd expect if dark matter halos can pass through each other without interacting, while gas clouds collide and slow down. It's very difficult to explain this observation without invoking dark matter. Understanding dark matter and how it drives structure formation is crucial for interpreting observations like the Hercules-Corona Borealis Great Wall. The gamma-ray bursts we see are the visible tip of the iceberg. Beneath them, invisible but influential, is an enormous concentration of dark matter, perhaps 10 or 20 times more massive than all the visible galaxies in the region. This dark matter provided the gravitational framework that allowed those galaxies to form, that collected the gas from which their stars were born, and that continues to hold the structure together against the universe's expansion. The debate and controversy. Not everyone is convinced that the Hercules-Corona Borealis Great Wall is real. Since its discovery in 2013, the structure has been the subject of vigorous scientific debate. with some astronomers arguing that it represents a genuine feature of the universe's large-scale structure, while others suggest it's a statistical artifact, a pattern that appears meaningful but is actually just random chance. The skeptics raise several concerns. First, there's the fundamental issue that the structure is too large to exist according to current cosmological models. While unexpected discoveries can certainly force us to revise our theories, the principle of parsimony suggests we should first exhaust all other explanations before concluding that our fundamental understanding of the universe is wrong. Could there be some more mundane explanation for the clustering of gamma-ray bursts in this region of sky? One possibility is selection bias. Gamma-ray bursts aren't evenly distributed across the sky, even in a uniform universe, because our ability to detect them and measure their distances isn't uniform. Some regions of the sky are obscured by our own galaxy's dust and gas, making it harder to detect gamma-ray bursts there. Some regions have been observed more intensely than others simply because of how telescope time has been allocated. Perhaps the Hercules-Corona Borealis Great Wall appears more prominent than it really is because we've observed that region more thoroughly than other parts of the sky. The Discovery team addressed this concern by carefully accounting for survey selection effects. They showed that the clustering remains statistically significant even when potential biases are included in the analysis. But critics point out that accounting for all possible biases is difficult, and subtle effects might remain that could explain at least part of the observed clustering. Another concern involves the statistical methods used to detect the structure. When you divide a dataset into multiple subsets and search each one for unusual patterns, you increase the chances of finding something that looks significant just by chance. This is called the look elsewhere effect or multiple testing problem. Imagine flipping a coin 10 times and getting 7 heads. That might seem unusual, but if you flip 10 coins and look for any set of 10 flips that produces something unusual, your chances of finding at least one set with 7 heads increase dramatically. The original analysis divided gamma-ray bursts into 9 different redshift ranges and looked for clustering in each range. The Hercules-Corona Borealis Great Wall was detected in one of these ranges, from redshift 1.6 to 2.1. Sam Christian's 2020 paper argued that when you properly account for having looked at 9 different ranges, the statistical significance of the finding decreases substantially. Instead of a 2% chance of being random, it might be more like 10 or 15%. Still unusual, but not definitive proof. Horvath, Hakila, and their colleagues responded to these criticisms with additional analyses. They pointed out that the clustering doesn't just appear in one redshift bin. There's evidence for it across a broader range, and the signal has actually gotten stronger as more gamma-ray bursts have been added to the sample over the years. If the structure were just a statistical fluke, adding more data would tend to wash it out, making it look more like random noise. The fact that it persists and even becomes more prominent suggests it's real. The 2025 study took this further, using improved statistical techniques and a larger dataset to show that the Great Wall might extend from redshift 0.33 to 2.43, a much broader range than originally thought. This extended range is harder to dismiss as a statistical artifact because it involves gamma-ray bursts across a wide span of cosmic history, all clustering in the same general region of sky. But there's another layer to the debate that goes beyond statistics. Even if the clustering is real and not a statistical fluke, what does it actually mean? Does it represent a single coherent structure, A massive wall or filament of galaxies stretching 10 or 15 billion light years? Or could it be several smaller structures that happen to be aligned along our line of sight? Imagine looking at a string of pearls edge-on. From your perspective, the pearls might appear to merge into a single long structure. But if you could view them from a different angle, you'd see that they're actually separate beads arranged in a line. The Hercules-Corona Borealis Great Wall might be similar. The gamma-ray bursts might trace several separate galaxy filaments that appear connected when viewed from Earth, but aren't actually physically linked in three-dimensional space. This is a difficult question to answer with current data. Measuring positions on the sky is relatively easy, but determining precise three-dimensional positions requires accurate distance measurements, and distances in cosmology always have some uncertainty. The redshift-distance relationship depends on the universe's expansion history and its overall geometry, both of which have some uncertainty. More fundamentally, peculiar velocities, the motions of galaxies through space due to local gravitational effects rather than cosmic expansion, can introduce errors of hundreds of millions of light years in distance estimates. To definitively prove that the Hercules-Corona Borealis Great Wall is a single coherent structure, astronomers would need to map it in 3 dimensions with high precision. They'd need to show that the gamma-ray bursts and their associated galaxies are part of a connected network of filaments, not just aligned by coincidence. This requires not just more gamma-ray bursts, but more complete coverage of the region, filling in gaps in the current data. This is where the proposed Theseus mission becomes crucial. Theseus would detect gamma-ray bursts across the entire sky with unprecedented sensitivity, providing a much more complete census of these events. It would be particularly good at detecting gamma-ray bursts from the early universe, at high redshifts, where current instruments struggle. With data from Theseus, astronomers could map the three-dimensional distribution of gamma-ray bursts in the Hercules-Corona Borealis region, with enough detail to determine whether they trace a single structure or multiple separate structures. Unfortunately, Theseus hasn't been selected for final development yet. It's competing with other mission proposals for limited funding, and it's unclear whether and when it might fly. In the meantime, astronomers are working with the data they have, refining their analyses and searching for additional evidence. Some of this evidence comes from other tracers of large-scale structure. While gamma-ray bursts are the primary tool used to identify the Hercules-Corona Borealis Great Wall, astronomers have also looked for concentrations of quasars, galaxies, and other objects in the same region. If the structure is real, these other tracers should show clustering as well, providing independent confirmation. The results are mixed. Some studies have found evidence for clustering of quasars and galaxies in the direction of the Great Wall, supporting the idea that it's a real structure. Other studies haven't found statistically significant excess. The discrepancies might be due to differences in the samples used, the statistical methods employed, or simply the difficulty of detecting subtle clustering signals in noisy data. The debate over the Hercules-Corona Borealis Great Wall highlights how science works at the frontiers of knowledge. When something unexpected is discovered, especially something that challenges fundamental theoretical predictions, it's appropriate and necessary to be skeptical. Scientists must examine the evidence carefully, consider alternative explanations, and demand rigorous proof before accepting that a discovery is real. This skepticism isn't cynicism. It's a vital part of the scientific process that helps prevent false conclusions and ensures that our knowledge rests on solid foundations. At the same time, discoveries that challenge existing theories are often the most important ones. If the Hercules-Corona Borealis Great Wall is real, and as large as current estimates suggest, it would force cosmologists to reconsider fundamental assumptions about how structure forms and how the universe is organized. This potential for revolutionary insight is what makes the debate so intense, and why astronomers on both sides are so invested in resolving it. For now, the question remains open. The Hercules-Corona Borealis Great Wall might be the largest structure in the universe, a cosmic feature so vast it defies theoretical prediction. Or it might be a statistical mirage, a pattern in the noise that looks meaningful but ultimately isn't. Only better data and more detailed analysis will provide the answer, and the wait for that data continues. Implications for cosmology. If the Hercules-Corona Borealis Great Wall is confirmed to be real and as large as current estimates suggest, the implications for our understanding of the universe would be profound. A structure 10 to 15 billion light-years across, more than 12 times larger than the supposed theoretical maximum, would represent a serious challenge to the cosmological models that have been successful in explaining so many other observations. The most immediate implication would be for the cosmological principle itself. This principle, remember, states that the universe is homogeneous and isotropic on large scales. It's not just a convenient assumption that makes calculations easier. It's a philosophical statement about the nature of the cosmos, an extension of the Copernican idea that we don't occupy a special place. If structures as large as the Hercules-Corona Borealis Great Wall exist, it becomes harder to maintain that the universe is statistically uniform. However, before declaring the cosmological principle dead, we need to be careful about what large scales means. The principle doesn't require the universe to be perfectly smooth at all scales. It only requires homogeneity when averaged over sufficiently large volumes. Perhaps the scale at which homogeneity emerges is larger than we thought. Instead of a few 100 million light-years, maybe it's a few billion light-years. The Hercules-Corona Borealis Great Wall would still be exceptionally large, but not necessarily a fatal problem for the principle if we're willing to adjust our definition of what counts as a large scale. This revision wouldn't be trivial. It would require rethinking some of the theoretical underpinnings of modern cosmology. The scale at which the universe becomes homogeneous is related to the cosmic horizon in the early universe, the maximum distance over which different regions could have been in causal contact and thus able to coordinate their properties. If structures larger than the horizon scale can form, it suggests that either our understanding of the early universe is incomplete or that processes we haven't considered are at work. Another possibility is that the cosmological principle remains valid, but our models of structure formation need adjustment. Perhaps the initial density fluctuations from inflation were larger or distributed differently than standard models predict. Perhaps dark matter has properties we haven't accounted for, allowing it to form larger structures than we thought possible. Perhaps dark energy, which is currently thought to have been negligible in the early universe, actually played a role in structure formation at earlier epochs than we realized. Each of these possibilities would require changes to the standard model of cosmology, the lambda CDM model that has been so successful at explaining observations. Lambda CDM describes a universe dominated by dark energy and cold dark matter, with structure forming, from Gaussian random fluctuations produced during cosmic inflation. This model explains the cosmic microwave background's properties, the large-scale distribution of galaxies, the abundance of different elements, and many other observations with impressive precision. But lambda CDM isn't perfect. There are several tensions and anomalies that have emerged as observations have become more precise. For instance, different methods of measuring the universe's current expansion rate, the Hubble constant, give slightly different answers. This Hubble tension might indicate that something is missing or wrong in our models. The Hercules-Corona Borealis Great Wall could be another piece of evidence pointing toward the need for revision. Some cosmologists have suggested that the solution might involve modified gravity. Instead of dark matter, perhaps gravity behaves differently on very large scales than Einstein's general relativity predicts. These modified gravity theories, like modified Newtonian dynamics, or its relativistic extensions, were originally proposed to explain galaxy rotation curves without invoking dark matter. Most cosmologists are skeptical of these ideas because dark matter successfully explains so many other observations, but modified gravity theories remain an active area of research. Could modified gravity explain the Hercules-Corona Borealis Great Wall? It's not clear. These theories would need to explain not just why such a large structure exists, but also all the other successful predictions of lambda CDM, from the cosmic microwave background to the abundance of elements produced in the Big Bang. That's a tall order, and no modified gravity theory has yet achieved this comprehensively. But if the wall forces us to reconsider fundamental assumptions, all options must be on the table. Another intriguing possibility is that the wall tells us something about the nature of dark matter itself. Cold dark matter is cold in the sense that the particles move slowly compared to the speed of light. But there are other possibilities. Warm dark matter particles move faster, and this affects how structures form. Warm dark matter would suppress the formation of small structures while potentially allowing larger structures to form more easily. Could a warm dark matter model explain the Hercules-Corona Borealis Great Wall while remaining consistent with other observations? Current constraints on dark matter properties from observations of the cosmic microwave background and the Lyman alpha forest, a technique that uses distant quasars to probe the distribution of hydrogen in the early universe, favor cold dark matter. But these constraints have some wiggle room. It's possible that dark matter is slightly warmer than the coldest models predict, and this might allow for the formation of larger structures than pure cold dark matter would permit. There's also the question of what the wall tells us about cosmic inflation. Inflation is the hypothesis that the universe underwent a period of exponential expansion in its first fraction of a second, growing from quantum scale to astronomical scales almost instantaneously. This expansion amplified quantum fluctuations to cosmic scales, creating the density variations that seeded all future structure. The amplitude and distribution of these fluctuations are predicted by models of inflation and constrained by observations of the cosmic microwave background. If the Hercules-Corona Borealis Great Wall is real, it might indicate that the fluctuations were larger or more variable than standard inflation models predict. This could point toward specific inflation models, or even suggest that something beyond inflation was at work in the early universe. Some physicists have proposed alternatives to inflation that might produce different patterns of initial fluctuations. Cyclic models, where the universe goes through repeated cycles of expansion and contraction, or bouncing models, where the Big Bang was actually a big bounce from a previous contracting phase, could potentially create different initial conditions that might allow for larger structures. These ideas are speculative and face significant theoretical challenges, but the Hercules-Corona Borealis Great Wall might provide an observational constraint that helps evaluate them. It's also worth considering that the wall might not require any fundamental changes to our models. Perhaps it's simply a rare statistical fluctuation allowed by the models, but extremely unlikely. Imagine rolling dice. Getting all sixes is unlikely but not impossible, and if you roll enough times, eventually it will happen. The universe is vast, and we're only seeing a fraction of it. Perhaps in the portions we can observe, we just happen to have gotten lucky and seen one of the rare, large fluctuations. This statistical explanation is unsatisfying because it requires accepting that we live in an unusual region of the universe, which goes against the spirit of the cosmological principle. But unsatisfying doesn't mean wrong. The universe doesn't care about our aesthetic preferences. If large structures like the wall are possible but rare in the standard model, and we happen to observe one, that's just how it is. Whatever the explanation turns out to be, the Hercules-Corona Borealis Great Wall reminds us that cosmology is still a work in progress. Despite tremendous advances in observational technology and theoretical understanding, we're still discovering basic facts about the universe's structure. Every new discovery has the potential to confirm our models or force us to revise them, and that's what makes cosmology such an exciting and dynamic field. The universe's largest structures compared. To fully appreciate where the Hercules-Corona Borealis Great Wall stands in the hierarchy of cosmic structures, it's worth comparing it to other megastructures that astronomers have discovered over the past few decades. Each of these represents a milestone in our understanding of the universe's large-scale organization. The story begins with the CFA-2 Great Wall, discovered by Margaret Geller and John Huchra in 1989. This structure, measuring roughly 760 million light-years long, 200 million light-years wide, and 15 million light-years thick, was revolutionary at the time. It was larger than any structure astronomers had previously identified, and provided the first clear evidence that galaxies were organized into walls and filaments surrounding voids. The CFA-2 Great Wall showed that the universe's structure extended to scales much larger than galaxy clusters, forcing cosmologists to think about how such large features could form. For more than a decade, the CFA-2 Great Wall held the record as the largest known structure. Then came the Sloan Great Wall, discovered in 2003 using data from the Sloan Digital Sky Survey. At 1.37 billion light-years in length, and located about 1 billion light-years from Earth, the Sloan Great Wall was roughly twice as long as its predecessor. It consists of a vast network of galaxy clusters and superclusters connected by filaments, forming a coherent structure that spans a substantial fraction of the observable universe at that distance. The Sloan Great Wall is located in the constellations Corvus, Hydra, and Centaurus. It includes several well-known galaxy clusters as part of its structure, including parts of the Corona Borealis supercluster, the Coma cluster, and portions of the Io supercluster. These clusters are connected by filaments dense with galaxies, creating a sheet-like structure that marks the boundary between two enormous cosmic voids. Interestingly, the Sloan Great Wall wasn't technically a gravitationally bound structure. The galaxies within it are moving apart due to the universe's expansion, and eventually, in the distant future, the wall will dissolve as the expansion separates its component clusters. This is true of most large-scale structures. Only the densest parts, the galaxy clusters themselves, are gravitationally bound. The walls and filaments are more like temporary concentrations in the flow of matter through space, persistent but not permanent. Next came the huge large quasar group, discovered in 2012. Quasars are the brilliant cores of active galaxies powered by supermassive black holes consuming material at tremendous rates. They're among the brightest objects in the universe and can be detected across enormous distances. The huge LQG is a collection of 73 quasars clustered together in a region about 4 billion light-years across. Located approximately 9 billion light-years from Earth, it was the first structure to seriously challenge the theoretical maximum size of about 1.2 billion light-years. The discovery of the huge LQG sparked debate similar to what we have seen with the Hercules-Corona Borealis Great Wall. Some astronomers questioned whether the quasar clustering was statistically significant or just a chance alignment. Others argued that even if the clustering was real, it might not represent a single coherent structure. These debates highlight how difficult it is to definitively identify and characterize structures at such enormous scales. In 2015, astronomers announced the discovery of the giant GRB ring, a roughly circular arrangement of 9 gamma-ray bursts at a distance of about 7 billion light-years. The ring has a diameter of roughly 5 billion light-years, larger than the huge LQG. Its circular shape is particularly puzzling because there's no obvious physical reason why gamma-ray bursts should arrange themselves in a ring. Some astronomers have suggested the ring might be an artifact of how we're viewing a three-dimensional structure projected onto the two-dimensional sky. But its nature remains mysterious. The South Pole Wall, discovered in 2020, is another massive structure, roughly 1.37 billion light-years long, comparable to the Sloan Great Wall. What makes the South Pole Wall particularly interesting is its proximity. It's located only about 500 million light-years from Earth, which in cosmological terms is quite nearby. The reason it wasn't discovered earlier is that it lies partially behind the zone of avoidance, a region of sky obscured by our galaxy's disk, making it difficult to observe. The South Pole Wall's discovery came from mapping peculiar velocities, the motions of galaxies due to local gravitational effects rather than cosmic expansion. Galaxies are pulled toward mass concentrations, and by measuring how they move, astronomers can infer where large structures lie, even in regions partially obscured by foreground material. This technique revealed the South Pole Wall's presence, showing that even in our local cosmic neighborhood, we're still discovering major structures. Then there's the Boss Great Wall, discovered in 2016 using data from the Baryon Oscillation Spectroscopic Survey. This structure, located between 4.5 and 6.5 billion light-years away, has an estimated mass about 10,000 times that of the Milky Way, and stretches roughly 1 billion light-years. Like the Sloan Great Wall, it's not a single coherent object, but rather a complex of superclusters and filaments connected in a network. Finally, we come to the Hercules-Corona Borealis Great Wall, the structure that dwarfs all others. At 10 to 15 billion light-years across, it's more than twice the size of the huge LQG, nearly 3 times the size of the giant GRB ring, and roughly 7 times larger than the Sloan Great Wall. If the current estimates are correct, It represents about 16% of the diameter of the observable universe, a staggering fraction for a single structure. What makes the Hercules-Corona Borealis Great Wall different from these other structures isn't just its size. It's also the method of its discovery. While most of these structures were found by mapping galaxies or quasars, the Great Wall was discovered through gamma-ray bursts, which are transient events rather than persistent objects. This means the structure we're seeing is traced by explosions that happened billions of years ago, providing a snapshot of the distribution of star-forming galaxies at a particular epoch in cosmic history. The Great Wall's extreme distance, about 10 billion light-years, also sets it apart. We're seeing it as it existed when the universe was less than 4 billion years old, much younger than the structures like the Sloan Great Wall that exist in the more nearby, more recent universe. This has important implications. It suggests that enormous structures could form relatively early in cosmic history, which is challenging for models that predict structures should grow gradually through hierarchical merging. Comparing all these structures reveals a pattern. As observational techniques have improved, and as surveys have mapped larger and more distant volumes of space, we've continued to find larger and larger structures. Each discovery has pushed against the theoretical maximum, and each has sparked debate about whether our models need revision. The Hercules-Corona Borealis Great Wall is the latest and largest in this sequence, but it's unlikely to be the last. Future surveys, particularly those using next-generation radio telescopes and space-based observatories, will map the universe in even greater detail and to even greater distances. They'll likely discover more enormous structures, and each discovery will provide new tests of our cosmological models. Whether these future discoveries will support the reality of the Hercules-Corona Borealis Great Wall, or suggest that our current interpretation of the data is misleading, remains to be seen. The mystery continues. As we draw this journey through the cosmos to a close, let yourself settle even deeper into relaxation, feeling the weight of these immense structures and distances dissipating like morning mist. The Hercules-Corona Borealis Great Wall, whether it's ultimately confirmed or refined by future observations, represents something profound about the universe and about the human quest to understand it. The Great Wall stands as a testament to how much we've learned and how much we still don't know. We've mapped the universe from the smallest subatomic particles to the largest cosmic structures. We've traced the universe's history from the first fraction of a second after the Big Bang to the present day, 13.8 billion years later. We've discovered that most of the universe is made of mysterious dark matter and dark energy, substances we can detect through their effects but can't yet directly observe. And we've found structures so vast that they challenge our theoretical predictions, forcing us to question our assumptions and revise our models. The controversy surrounding the Great Wall isn't a flaw in science. It's a feature. It shows that scientists are willing to debate, to question, to demand evidence before accepting extraordinary claims. The fact that more than a decade after its discovery, astronomers are still arguing about whether the structure is real and how large it might be, demonstrates the rigor and care with which science approaches its questions. Current research continues on multiple fronts. Astronomers are analyzing new gamma-ray burst data as it becomes available, refining their statistical methods, and looking for additional tracers of large-scale structure in the same region of sky. They're comparing observations of the Hercules-Corona Borealis Great Wall region with predictions from ever more sophisticated computer simulations that model the universe's evolution in unprecedented detail. They're measuring the properties of other large structures, looking for patterns that might explain why some structures grow so large. The next major breakthrough may come from the James Webb Space Telescope, which can observe distant galaxies with extraordinary sensitivity, or from future radio telescope arrays like the Square Kilometre Array, which will map cosmic structure through hydrogen emission. Or it might come from the proposed Theseus mission, if it's approved and launched, providing the comprehensive gamma-ray burst observations needed to definitively map the structure's three-dimensional extent. Whatever future observations reveal, the Hercules-Corona Borealis Great Wall has already accomplished something important. It's reminded us that the universe is capable of surprises, that nature is under no obligation to conform to our theoretical expectations, and that discovery is a continuing process, not a destination reached. Beyond the scientific implications, there's something deeply moving about contemplating structures on these scales. We live on a planet that's a tiny speck orbiting an ordinary star in a vast galaxy, which is itself just one of hundreds of billions of galaxies strung along filaments in the cosmic web. And some of those filaments, like the Hercules-Corona Borealis Great Wall, stretch across distances so vast that light takes 10 billion years to cross them. Our human minds weren't evolved to comprehend such scales. We evolved to navigate a world measured in meters and kilometers, in days and years. The fact that we can nonetheless discover these structures, measure them, debate their properties, and try to understand how they formed is a remarkable achievement of human ingenuity and curiosity. As you drift toward sleep, let yourself imagine the cosmic web, that vast network of filaments and walls surrounding voids, all built by gravity from tiny quantum fluctuations in the universe's first moments. Imagine the Hercules-Corona Borealis Great Wall stretching across billions of light years, traced by the brilliant explosions of dying stars whose light has traveled for most of cosmic history to reach our telescopes. Imagine the dark matter that provides the invisible scaffolding for all this structure, and the dark energy that's currently accelerating the universe's expansion, stretching the cosmic web even as we observe it. The universe is a place of wonders beyond imagining, of structures that dwarf our comprehension, of processes that operate on timescales unimaginably longer than a human lifetime. And yet, we're part of it, made of atoms forged in the cores of long-dead stars, living on a world that orbits a star that sits in a galaxy that's part of this vast cosmic structure. We're connected to it all, participants in the universe's grand story, observers trying to understand the immense stage on which we find ourselves. The mystery of the Hercules-Corona Borealis Great Wall continues. Future observations will tell us whether this structure is as large as current estimates suggest or whether our interpretation needs refinement. They'll tell us whether our cosmological models can accommodate such structures or whether fundamental revisions are needed. They'll reveal whether this is the largest structure we'll ever find, or whether even more enormous features await discovery in the depths of space. But regardless of what future observations reveal, the journey of discovery continues. Every question answered leads to new questions. Every mystery solved reveals deeper mysteries. That's the nature of science and the nature of the universe itself, an infinite source of wonder and puzzlement, always offering new frontiers to explore. So rest now. Let your thoughts drift like galaxies through the cosmic void, and know that tomorrow, somewhere, an astronomer will turn their telescope to the sky, searching for the next great mystery, the next impossible structure, the next revelation about the universe that surrounds us, and of which we are a small but wondering part. Before you drift off completely, if these cosmic journeys bring you peace and wonder, please remember to subscribe to the Science Pillow and leave a like on this video. Your support helps keep these explorations coming, bringing the universe's greatest mysteries to your bedside each week. Until next time, sleep well, dream of distant galaxies, and know that the universe is far stranger and more wonderful than we ever imagined.